Already linear functions. They were back in chapter 4, actually. Linear functions, and on your homework, do we have any linear functions on that homework you just corrected? Or any of them linear?
The first one.
The first one. That's the title of the worksheet, from linear to quadratic. We went from being a straight line to being quadratic, being a U-shaped graph. What do you think made that happen? Why? Anybody have any ideas why those other 5 turned out U-shaped and not a straight line? Kenzie?
Because in all of them except number 1 there is an x squared.
The degree of the polynomial that y was set equal to. Will you look at your homework and verify this? That the degree of the polynomial that y was set equal to is always a degree 2 when it's a U-shaped graph, whether it's a U that's opening up like this or one that's opening down. The degree of the polynomial that y was set equal to was always quadratic, it was always degree 2. Sometimes it was a binomial and sometimes it was a trinomial, but it was always degree 2, which we know is quadratic. But in number 1, why does it turn out linear? What's the degree of a linear function? 1. Degree 1 is a linear function, x to the first power. Are there any x squareds in number 1? No, there's only x's to the first power, so that's why that one turned out linear. So when we talk about quadratic functions, it's any function, equation. When we hear the word function, we can also think equation. That can be written in the standard form, y equals ax squared plus bx plus c. Which should look familiar from last chapter when we were factoring quadratic trinomials and binomials. And now it's just set into an equation set equal to y. And then a cannot equal 0. Anybody know why a maybe could not equal 0? I didn't make you SQ3R this one, so we have to do some thinking without, I'm going to guess most of you didn't read ahead. Why do you think a can equal 0, John?
Because anything times 0 is 0.
Okay, so if we took an x squared times 0, we would get 0, John says. Well, if you have 0 plus bx plus c, what do you have?
Bx plus c.
Bx plus c. If you have bx plus c, is it quadratic anymore?
No.
No, what is it now? What is it now?
Linear?
Linear.
Oh, yeah, it is.
Except we're used to hearing it in mx plus b, aren't we?
Yep.
But it could also be called bx plus c. It's okay. So it's linear then. So we need a to not be 0. Notice it does not say b can't be 0. It does not say c can't be 0. It says a can't be 0. Okay, so remember how I said it was such a big deal for us to be able to identify a, b, and c in that last chapter? Every function has a family. Every family has a parent. So the quadratic function what in the world? I think I had it right the first time. Function, F. Okay, so the most basic one of the quadratic family is called the parent function. And if it's the most basic, does anybody remember what the parent function was for the linear family?
Y equals x equals 0.
Y equals mx plus b is just slope-intercept form. Y equals 0 would be a horizontal line.
Which is standard form.
Y equals x. Oh, we forgot that. That was chapter 4. Y equals x is the linear family's parent function. So now, that's like a little giveaway. What do you think is the parent function then for the quadratic family?
Y equals x squared.
Y equals x squared. The most basic one, y equals x squared. Or remember, if a was equal to 0, we wouldn't have it. But what is a equal to for this one?
1.
What's b equal to?
0.
0. There are no x's. 0 times x, they're gone. Remember, we didn't say b can't equal 0. What's c?
0.
0. So we have the parent function, the most basic one, the one that we start from, and then things happen to that one. Now let's talk about the graph, because you already did some graphing of them today, and this is what should have happened. You should have gotten a smooth curve, and anybody know what that smooth curve's name is?
Parabola.
It's a parabola. For a linear function, it's a line. For a quadratic function, it's a parabola.
We just learned that term in science.
Did you?
Yeah, we're learning about trajectory and everything. Focus
Well,
on
that's
that.
going to be useful when we're studying this. Because when we have a parabola, there's two things that can happen. And there's two things that happened on your homework. Will you look at your homework and tell me what happened on the parabola ones? Do they all have the same behavior? No. What happened?
We're all different.
They're different. Some of them are fatter, skinnier, some are opening up and some are opening down. Well, we're going to talk about why do some open up and why do some open down. Look at the four that open up. And look at the the quadratic side, the polynomial side that is n equal to y, and tell me something that you say, well, you know what, this seems to happen every time. Can you identify anything that you think happens every time when they're opening up? Nita?
All the y values are positive.
All the y values are positive. They don't have to be though, but in this case I think they always were, weren't they? Oh no, there were. There were sometimes there were negative y values. I'm looking at some graphs now, and I see there were sometimes there were negative y values. Well, look at here. This is kind of like a giveaway right here. The A value controls whether it opens up or it opens down. 4 of them opened up. Tell me something about the A value for all 4 of those. What do they have in common? They're greater than 0. They are positive numbers. So when you have A greater than 0, or in other words, a positive A value, you better count on it opening up. If your graph doesn't open up and there was a positive A value, there's trouble. There's a problem. You should say to yourself, something's not right. Well then, there's only one on your homework that opened down. Tell me something about the A value for that one.
Negative.
It's a negative. So when A is less than 0, also known as negative, it will open down. So that's behavior we can count on. Now notice, we can't, and we did this back when we were in chapter 6 and we were factoring quadratic trinomials, factoring quadratic binomials. I said, make sure that you put them in standard form first, and then we'll go to word factoring. Same thing here. Don't identify A unless your quadratic is put in standard form and there's only a y on the other side. It better be y equals a quadratic in standard form. Then you can identify your A. Then you can say, oh, this is what should happen. It should open up or it should open down. Well then, every one of those graphs on your homework changed direction. They were going one way and then they stopped, made a turn, and bounced back up the other way. Did that not happen? And when that one that opened down, was it not climbing for a while and then all of a sudden it stopped and it went back down? What did you learn in science? Is there something that has a parabolic behavior? Just told me.
Projectile.
A projectile. Like, give me an example of a projectile.
Like
Throwing
someone throws
stuff
throwing a football or a frisbee.
Throwing a football. You throw a football, what happens? If you're a pretty good thrower.
It goes up,
It goes
reaches
up.
its peak, and then it goes back down.
It reaches its peak and it comes back down again. It has a peak. Okay? So it has parabolic, even if it doesn't make a full-fledged parabola, it at least starts somewhere at where your hand is, and then it goes like this, and then it goes down to the ground. So it has part of that parabola curve, doesn't it? And it has a peak. Then there's also, what if I was standing up here and we took that screen out and I threw something out the window, and I didn't just drop it straight down, I just threw it. I wanted, Mrs. Belkey's over there in her car, and I'm like, here, catch Mrs. Belkey. What would happen?
It would go for a little while, it would reach its peak, and then it would fall.
Same thing, yeah, it would go for a while, it would reach its peak. Hopefully I do it like this, and it would reach its peak, and it would come back down and have the same behavior. Okay, give me an example of something that would have the opposite behavior. In other words, it would come down, and then it would go back up. Pardon?
Bouncing a ball.
Bouncing a ball,
Or a yo-yo.
a yo-yo.
Bird, or they come, they swoop
A
down.
bird who swoops down and then flies back up. So, Jake?
What about like one of those things that are like weird and then like boomerang? throw it and it comes back at you?
Oh, we have a boomerang, is that what they're called, boomerangs, yeah?
Yeah. I have.
So what happens is, whenever we have behavior that, whatever it is, like, let's say I have a golf ball and I drop it from this window. Instead of throwing it, I drop it. What's it gonna do? It's gonna bounce, it's gonna hit the ground, and then it's going to come back up.
Back up here.
Jade says it's gonna explode. Well, I don't have that much force, trust me. It's going to hit the ground, it's gonna bounce back up, and it's gonna come back up, not all the way to me probably, because I don't have that good of force, but so there's lots of things that have parabolic activity, and they either reach a peak because they're going up and reaching that peak and then coming back down, or they reach a minimum, they can't go any lower, and then they come back up. That's important things about quadratic behavior. It changes direction at that point where it reaches its peak or reaches its lowest point at what's called a vertex. Where does it turn? Where does the behavior change? Right at that point, it says, stop, I'm going to change behavior now. At the vertex. When the parabola opens up, the y value, why do I say y value? Because peak, lowest point, that's up and down. Which ones goes up and down on our coordinate plane?
The y-axis.
The y. So the y value, when the parabola opens up, the y value of the vertex, so it's opening, so when it opens up, and the y value is down here in the vertex, would that be the maximum or the minimum? That'd be a minimum. The y value is considered the minimum. So the y value of that point right there, we don't know what it is, this y value would be called a minimum. When the parabola opens down, that's one of those throw the football, it reaches a peak, it comes back down. The y value of the vertex is called a
Max.
maximum. That's as high as it goes. So again, we have this vertex here. It is ordered pair x, y. Its y value is considered the maximum. Whatever the y value of that vertex is, this is just a generic one. So we know A controls, right now this is what we know. A controls whether it opens up or it opens down. The vertex tells us whether it's going to have a minimum or a maximum, and it gives it to us by looking at the y value. The other thing we are going to talk about is that the imaginary line that's not really drawn there, but that divides the parabola into two symmetric halves. If you look on your homework, every single point on those U-shaped graphs, every single point on those U-shaped graphs except the vertex should have a point that's symmetric to it. It's across an imaginary line. In other words, it has another one over on the other side that matches up with it. Equal distance. If we drew an imaginary line through it, they would be equal distance from that imaginary line. Anybody know what that imaginary line is called?
Equator.
It's not called the equator, but on the earth it is, you know? But do we have symmetric cities on the earth?
Which?
Not really, but we do have symmetric locations probably on the graph. If it's not an equator, it's three words. Axis of symmetry. It's a vertical line, always a vertical line that cuts the parabola in half. Well, if it cuts the parabola in half, what's it going to always have to go through?
The vertex.
It's always going to have to go through that vertex. Always going to have to go through that turning point. Okay? So those are just some characteristics. Now, again, I did not make you F3R, and we're not going to do everything here in these notes. notes that you might have come across in your homework, so what should you do?
Do it anyways.
Refer to your text, you know, that text that you could still refer to, still read, or SQ3R on your own. Okay. Sometimes we don't have a graph. We're just going to identify if a function is quadratic given an equation. The first thing you always have to do, if it isn't already done, is get y alone. Y's got to be by itself. The other side needs to be written in
Standard form.
standard form. I already addressed that. Determine then if it is of this form. Y equals ax squared plus bx plus c. Where what? A does not equal 0. Can equal 0. Can B equal 0?
Yes.
Yeah. Can C equal 0?
Yes.
Yeah. Just A can. So how we show work here in the notes, we show work in the homework. Okay? Is y alone in number 1?
No.
What are we going to do?
Minus 6x.
Subtract 6x. Now we have y equals negative 14, take away 6x. Is the y's alone, is that standard form on the other side? No. So what would standard form look like? Let's change this to add the opposite here.
6x squared.
Negative
Negative 6x.
6x, there's no square there, is there?
Oh,
I thought I had.
Plus
Never mind.
negative 14.
negative 14. Is it quadratic?
No.
Why not? It's linear, isn't it? It's not quadratic, so that's what we would put, not quadratic. Because A equals what?
6.
A equals 0.
Oh, yeah.
B would equal negative 6. A equals 0 for this one. It's not quadratic. A equals 0. Therefore, best we can say this is linear because it's degree 1, so it's not quadratic. Okay, you try number 2 now. Get in y by itself, standard form on the right side. Identify A. If you can identify A, you might as well keep going and do B and C also. And then decide what's the deal. Do you agree with me so far?
Yes.
Okay. What are we thinking? Can we identify A? What is A?
A is negative 2.
A is negative 2. Oh, so if we did have to graph this, we'll maybe be able to say something else. B equals 3, C equals negative 1. We can identify A, B, and C. We say it is quadratic.
A equals -2.
Since A equals negative 2, tell me something about this graph if we
It
did graph
opens
it.
down.
It would open down. It would have a minimum or a maximum?
Would have a
A
maximum.
maximum. It would have a maximum, that's right. Okay. Would it have a vertex?
Yes.
Every parabola has to have a vertex, doesn't it? Has to have. Okay. Any questions on being able to do it from an equation and what you need to show? Okay, what if they just give us a table of values? We don't have an equation. We don't want to graph it because LeBron didn't provide a coordinate plane for you and you're like, I don't want to go through that much work and make my own. So to identify if a table of values or a set of ordered pairs represents a quadratic function, we're going to look for a common
Factor.
second
Oh, snap.
difference. We're going to look for a common second difference in y Okay, let's recall again, let's see, I know eventually I'm gonna get something out of you with that before, I know I am. What made a function linear from a table of values?
If they had the same pattern all across the table.
If it has a constant change in x
And a constant change in y.
and a constant change in y called a common difference.
Oh, yeah.
So it happens right away. If there's a common first difference, it's linear. But if there's not a common first difference, now you have to take it a step further because you're getting more advanced and you have to say, okay, now I'm going to check to see if it's quadratic. Because if it has a common second difference, now I can say, oh, this would be a parabola. This is a quadratic function. But remember, we still always have to look for that constant change in x also. So is there a constant change going on here in x?
Yes.
What's it doing?
Adding by one.
It's adding up. It's adding up by 1 each time. There's a constant change of +1 every time. So we're cool. We're like, okay, I'm gonna go check out the y's now. So we're gonna check out the first difference in y's. We don't multiply, we say, what do I have to do? Add or subtract and how much? So to get from 39 to 18, what do I have to do?
Subtract
Subtract
minus
21
and this minus 15.
to go from 18 to 3, subtract 15. 3 to -6,
Minus,
Nine.
subtract 9.
like I got lost.
Minus 3.
And the next one is subtract 3. Is it linear?
No.
No, there isn't a common difference there. None of those look alike. So now we say, okay, it's not linear. I'm a more advanced student now. I have to move on. I don't get to say this is not linear. I now I'm going to check to see if it is quadratic. So we get from -21 to -15. Careful. Add 6. Now we're going up.
What?
Well, it's 21 below, it went up to 15 below. Didn't the temperature go up?
No.
Yes.
15 below to 9 below.
Plus 6.
Up 6.
What is this?
9 below to up to 3 below.
Plus 6.
Up 6. Oh, it's the same. So there is a common second difference. So we can say that this is what?
I got it.
Is a quadratic function, is quadratic. We have no idea what the equation is right now, and by the way, someday you will learn how to write an equation for that table, but right now, you're not gonna go there. Okay. So, anybody have questions? Do you get to just put yes or no answers on your homework, do you suppose? If you're gonna say that a parabola opens up, you better say that A equals whatever it equals, and it better be what then?
Positive.
A positive number. So if it's 3, you would say A equals 3, then you could say opens up. So you write that. You don't just say up. What supports your up?
I got a question. Will we ever have to do that more than twice?
Oh yes, there's another time, but not this year. If you don't find a common second difference, then you keep going and you try something else. Anybody think they know what the next one would be?
Scatter
If
plot.
there was a common third difference, if there's a common first difference, it's degree 1 linear. If there's a common second difference, it's degree 2 quadratic.
Forms a triangle.
If there's a common third difference, there's a degree 3, which is, no, that's the number of terms.
A triangle.
Degree 3, oh, you've gotten already, cubic.
Cubic, yeah, that's the word.
That would be a cubic function.